This video is part of the MCAT Chemistry video course. Subscribe and hit the bell if you'd like notifications about the release of new videos, and please visit ancientbrainstutoring.com for questions about one-on-one virtual MCAT tutoring. In this video, we'll cover entropy and Gibbs free energy. Throughout this video, we'll talk a lot about changes in enthalpy, changes in entropy, and changes in free energy. Those three things are changing during the process of a chemical reaction, and each one of them can either be positive or negative. Whatever sign you have for that particular chemical reaction, if you then go in the reverse direction, then that sign is going to be flipped. So for example, if we have a reaction and we say that the entropy goes down, if we go in the reverse direction for that reaction, then the entropy will go up when you go in the reverse direction. Later in the video, we'll talk about favorability. So if a forward reaction is unfavorable, then that means that the reverse reaction will be favorable. And you can apply that to delta S, delta H, and delta G. In the last video, we went over enthalpy, and in this video, we're going to go over entropy and then combine those two things when we go over Gibbs free energy. Entropy is a measure of disorder. So as things become more disordered, we say that the entropy goes up. And you've probably heard before that the entropy in the universe is always increasing. The reason that entropy is increasing at all times in the universe is not due to any mysterious forces or any choice that the universe is making. It's simply due to probability. A good way to intuitively understand this is to think about whenever you're doing a load of laundry with a bunch of mixed colors, and then the clothes are just getting done with the dryer. Whenever you open the dryer, there's an almost guarantee that all those colors are going to be mixed up. And it's extremely, extremely unlikely that your clothes are going to be sorted by color whenever you open up the dryer. And the reason that is solely due to the fact that there are so many more combinations or different ways that your clothes can be arranged that would result in a mix-up of colors compared to how many combinations of arrangements of clothes that would give you your colors sorted out. And because there are so many different combinations that will end up in your clothes being mixed up by color, it makes that result so much more likely. And the mixed color result would be a more disordered configuration. So the universe tends to go towards disorder because there are so many more arrangements of molecules and things in the universe that are disordered compared to the amount of arrangements that would be ordered. Now we're going to go through some examples of how this gets applied to actual chemical equations and some ways that you'll see it applied on the test. The first and most common way you're going to see it is applying it to phase changes. And we're going to look at comparing a solid to a gas. A solid has such strong intermolecular forces that the molecules, which are represented by these red circles, are pretty much locked in place because they're strongly bound to the other molecules around them. So consider how many different combinations and arrangements of molecules would end up giving you a solid, and then compare that to something like a gas, where the molecules can just move around at will. So the gas obviously has way more combinations of arrangements of molecules that could still resemble a gas compared to the solid. So whenever you have more movement with your molecules in a substance, there's going to be higher entropy. That will be the most common way that they test it, and it has the largest effect on entropy. So really be on the lookout for any time you go from a solid to a liquid or a liquid to the gas. And a gas would have the most entropy, a liquid would have the second most entropy, and then a solid would have the least amount of entropy. Sometimes all the substances in a reaction may all be gases, or maybe they're all the same phase. So the next thing you want to look out for is the number of moles on each side of the reaction. So for this one, we have 2 moles of NH3, which is a gas, and it's decomposing into 1 mole of nitrogen gas and 3 moles of hydrogen gas. When everything is the same phase, the rule is whichever one has more moles, whatever side of the reaction has more moles, will have the higher entropy. And here's an image to help you think through this. Here would be 2 moles of NH3, or 2 molecules of NH3, and think about how many different ways can you arrange those compared to how many different ways could you arrange the 1 mole of nitrogen gas and the 3 moles of hydrogen gas. So hopefully you can see pretty easily that whenever you have more moles, there's just way more ways to arrange them, which then makes that outcome more likely and more disordered. Gibbs free energy combines the concepts of enthalpy and entropy to tell us which side of a reaction is most favorable. We're going to talk some about enthalpy here, so if you're unsure about that, make sure you go back and watch the previous video so that you're totally good on it. In that last video, we established that a negative delta H indicated that we went from a less stable reactant to a more stable product. And any time that you go from less stable to more stable, the more stable state is going to be favored. So a reaction that has a negative delta H compared to a positive delta H is going to be more favorable. And then we also just established that an increase or a positive delta S in entropy is favorable. So overall, whenever you have a negative delta H and a positive delta S, you're going to have the most favorable reaction. So if you look at our equation and you combine a hypothetical negative delta H with a hypothetical positive delta S, throw that into the equation, that's going to give you a negative delta G. And the sign of delta G, whether it's negative or positive, is ultimately what tells us if a reaction is favorable or unfavorable. And a favorable reaction is called spontaneous, and it will have that negative delta G because that either indicates that we have negative enthalpy and positive entropy, or it can indicate that either the decrease in enthalpy was so large that it overcomes a decrease in entropy, which that would be a negative delta H and a negative delta S because we said we decreased in entropy. But if our delta H term is large enough, it will overcome that decrease in entropy. So that would mean that our delta G could possibly still be negative if the delta H term is large enough or if the temperature is a small enough temperature. So that way we're multiplying the negative delta S by a small magnitude. So you'll see it commonly mentioned that a negative delta H and a negative delta S can still result in a spontaneous reaction at low temperatures. And I would also add or sufficiently large enough drop in enthalpy. There's one more combination of signs for enthalpy and entropy that can give us a negative delta G, and hopefully you can kind of see where we're going. So let's say we have a positive entropy, so it's not looking good for favorability right now, but we also have a positive delta S, and if that delta S term is large enough, or if the temperature is high enough, because we're going to multiply the delta S by it, then we will be subtracting a large enough value from the positive delta H that we still may be able to end up with a negative delta G. So that was high temps or a large increase in entropy. I would strongly suggest not memorizing this because if you need to memorize it, then I think it's a really big indicator that you're not really understanding it, because you should be able to think your way through what combinations of enthalpy and entropy would result in a spontaneous reaction. And then if you also have the equation memorized, which I would definitely recommend memorizing the equation, then you'll be able to think through what combinations would result in a negative delta G. And you can probably see that if we had a positive delta H and a negative delta S, then that would result in a positive delta G. And anytime you have a positive delta G, that's an unfavorable reaction and is non-spontaneous. What delta G is actually telling you is really similar to the change in enthalpy, so delta H. And remember that the change in enthalpy told us how much energy was gained or lost in the bonds of our molecules when we went from reactants to products. Delta G is taking that exact same concept and then also applying the entropy of the reactants versus products. And the sign of delta G tells you whether or not the reaction absorbed free energy from the surroundings or released free energy into the surroundings. And if that sounds extremely similar to the concept of enthalpy, don't let yourself get super wrapped into it, because the difference is extremely technical and it's not something at all that you need to understand for the test. All you need to really make sure you're good on is that delta H and delta G are slightly different, and delta G is just considering everything about delta H, but then also considering the change in entropy. And if that's the extent that you understand the true difference between those two, you're going to be totally fine. And in the next part of this video, we're actually going to look at a couple curves for delta G and compare those to delta H curves to point out the similarities and the differences and how they might test you on the two concepts. On the right side of our screen, we have a slightly new term. So it's delta G, but it has this symbol at the top. And that is indicating that this is the change in Gibbs free energy, but everything was at standard states. We talked in the last video about what standard states are, so go back and reference that if needed. The only two things we're going to add are that the temperature at standard state is 25 degrees Celsius, and anything that is aqueous, so any reactant or product that is in the aqueous form, will be at a concentration of 1 molar. So you just want to be aware that the delta G at standard conditions will always have this sign above it, and the delta G at those conditions may not be equal to the delta G at different conditions. So just be on the lookout during the test for that sign, so that way you know if you're working with standard conditions or not. And then just be really mindful of what's going on in the question and the passage and see if or if not that changes anything about how they want you to approach the question. Let's say hypothetically on the far left that you had a situation where they did give you the delta G naught. That's called delta G naught with that symbol above it. In order to be able to apply this equation here, you would need to have the change in enthalpy also at standard conditions and the change in entropy also at standard conditions. And that's just simply because you can't take, let's say, the delta H at one set of conditions and then apply the delta S at a different set of conditions and then combine those in the same equation. All of these values would have to be taken at the same conditions. So that would apply to standard states or even not standard states. That concept and this equation down here are both used to explain something that's really important. And that is when we are at standard states, if the KEQ is more than 1, then you have a spontaneous reaction, which would be a negative delta G. If your KEQ is less than 1, then you have a non-spontaneous reaction, or a positive delta G. We can explain this through two ways. One will be looking at this equation on the bottom, and then the other will be comparing Q and KEQ. So first, let's just look at this equation on the bottom. If you plug in a number that's over 1 for KEQ, then this term in the equation will become positive overall. So then combined with the negative at the beginning of that equation, then you're going to end up with a negative delta G. And then the opposite happens if the KEQ is less than 1 and you plug it into that part of the equation, then that term becomes negative. And then when that combines with the negative at the first part of the equation, then overall your delta G will end up being positive. And remember, it's only at standard state conditions that we can apply this equation because our delta G has that symbol there. The next way you can think about this is if you consider Q and standard state conditions, then we would plug 1 molar into each one of our values for Q. And regardless of what the exponents are, all of our terms would end up just being 1. So then Q would just give us a total of 1 every time at standard state conditions. And then if you think back to the equilibrium video, anytime Q was less than KEQ, the reaction would proceed to the right. So if KEQ is more than 1, then our reaction is going to proceed to the right whenever we're at standard state conditions because Q would be less than 1. And if a reaction is going to proceed to the right, then that tells us that that is a spontaneous reaction. Conversely, if KEQ is less than 1, then that means that our reaction quotient is already over the KEQ whenever we're at standard conditions. So now our reaction will not proceed to the right. So that would make the reaction non-spontaneous. Here are the two curves that you're going to see when talking about delta G. And you probably noticed that these are extremely similar to the curves that we see when talking about delta H or the change in enthalpy. So right now we're just going to highlight the similarities and the differences between these. First, the big similarity, and this is what can make it really confusing to conceptually distinguish between delta G and delta H, but this first similarity is that you will see the change from reactants to the transition state referred to as the activation energy, which is exactly what we see in those delta H graphs. And they also refer to that point in the curve as the transition state. And again, it really needs to be emphasized that you don't need to really understand why they use those terms for both delta H and delta G. Just remember that the delta G takes the delta H and then also considers the change in entropy. And then we're going to cover right now the differences that these graphs tell you compared to what the change in enthalpy graphs tell you. The first thing is that these graphs do not indicate whether you lost or gained heat. That would only be a delta H graph. What they do tell you, if we look on the graph on the left, when you go from reactants to products and you have a drop in delta G, that means your reaction is what we call exergonic and it released free energy. So it did not release heat, it released free energy, and that is a spontaneous reaction with a negative delta G. Conversely, on the graph on the right, anytime that we raise our free energy when we go from reactants to products, so that's a positive delta G, that one would be called an endergonic reaction because the molecules or the reaction absorbed free energy. So that's a non-spontaneous because it has a positive delta G. So the big difference is that these graphs of delta G tell you whether or not the reaction is spontaneous, and it tells you about the change in free energy, not the change in heat loss or heat gained. So the big difference between these graphs and the delta H graphs is that these ones are telling you if the reaction was spontaneous or not, and it's telling you the change in free energy. So underneath of our graphs, the molecules on the left one we would say that they lost free energy and the surroundings gained free energy. And then the opposite would be true for the graph on the right. The molecules gained free energy and then the surroundings lost free energy. And if going through these graphs was a little bit too fast and you're somewhat confused, go back and watch the video on enthalpy, because we went over these types of graphs but for enthalpy, and we did it much more in depth and explained more parts about them.